Anyway, so what were we doing? Equivariant something. So this is really, I think, the most amazing thing in one of the most amazing things in mathematics. It's sort of something that say, well, you'll see, in a very old subject, 19th century, lots of difficult ways of calculate things, and somebody came along and really saw how to, with some completely new point of view, where these calculations became very often elementary or doable, where they were completely impossible before. So I will try to, I'm not sure if I'll get to the actual formula. So there's a concrete formula that we'll be calculating, but maybe I will get there next time. We'll see. If I'm efficient, I'll get there now during this lecture. Okay, so let's just recall. So this is just repetition at the beginning. What we were doing. So the idea was the following. So I will now do really for what we are trying to do, it's sufficient to look at the simplest case of the group. So we will just look at this torus group, T equals C star. So that's the simplest thing, the simplest group that could act in this setup. And then we have some manifold X, which is some quasi-projective variety. And we assume that there is an action, and I'll note it this way, of T on X, right? So what we did last time was the following. So we defined the equivariant Chow groups, both cohomology and homology groups. And we define them approximately the following way. So equivariant Chow groups and so the idea was the following. We took an auxiliary space, and the point about this auxiliary space that the group acts on it freely, and well, anyway, actually it's not the conditions I'll not write down. The axioms, just what we did was the following. We took V, which was, well, let me even call it maybe V. No, I'll just call it V, which is just the vector space CL, right? And then we took, a space, well, not even give a notation for it. Of course, on CL, the group acts, say, T acts by just the usual equal weight. And so C star acts by the usual weights. And then we looked at the space CL minus the origin. And of course, that's an invariant subspace. And here the action is free. What was also important, I discussed this last time, that the codimension of what we threw away from CL should be small, and CL itself should be trivial, more or less. I mean, it's contractible space, or also as Chow groups of it are very simple, I mean, trivial, basically. So the action is free, and then we constructed this space X cross, so this CL, or maybe let's just call it V, it's a little bit shorter, U, and then we divided this by T, and we will just denote this by, say, XL T with some parentheses. And then in a certain sense, we could construct a space XT, which was just the limit as L went to infinity of this XLT. Okay, so this is, I didn't prove this directly, but we checked this in some examples. So this is not completely well defined. I mean, you can define it, but it's not the purpose. the idea is the following, that even though maybe this space is not so clear what it is, the Chow cohomology groups are, for example, are completely well defined in the limits. So they stabilize in a certain sense, in an obvious sense. So for example, we could look at just the example we looked at is was when x was a point. This was already interesting. Then this xlt, and so the x is now the point, is just the projective space. And then we define this, then this a t I of the point is just the limit as L goes to infinity of a I of p L minus 1. And of course, we know very well that this stabilizes. So of course, if L is small, then this is 0. But if L is large enough, then this will be just a one-dimensional space. And moreover, the ring, in a certain sense, which I also didn't specify, but it also stabilizes. So we actually, usually when you take this L, then the ring, you divide by the relation that x to the L is 0. But so maybe I'll write it even out. So this is the limit in a sense that I not specify completely precisely, but it's clear in our examples. So this was just z psi or zeta, z zeta divided by zeta to the power L. This is the Chow cohomology ring of PL minus 1. And of course, if you take the limit as L goes to infinity, it's quite natural to say that this is just z zeta. Okay. So in fact, the equivariant Chow groups are simpler than the finite ones. So I want to make a few remarks and maybe examples before I go on. So one remark that's a warning that's important is that so what the zeta so how to say this? There is so if you look at, for example, A0 t of a point, okay? So the A0 corresponds to the constant term, right? So this is just the constants in the polynomial ring, right? So this is because they have degree 0, okay? But what does it correspond to in the Chow group? So what is it here? What varieties, what element of the Chow group? So this, of course, stabilizes, corresponds to, say, 1 here. So the constants of 1. Which element? That's my question. So remember so we had this thing is that the normally AIX, so this just parenthetically, the lower one, so this describes cycles of dimension I, right, in X. So this was, and the upper one was just defined as a dimension of X minus I of X, which is just formally the codimension, then we intersected things, right? And this was the one that was a ring, okay? So the A0 is the top one. So yes, so the constant, so these are constants here. So for example, 1 in z zeta is just corresponds to, in this limiting thing, in each, it just corresponds to PL minus 1, the class of PL minus 1 in A0 of PL minus 1, right? At the top one, because codimension 0, so dimension top. So as just a point that one shouldn't confuse things. So I'm talking about stabilization here, but the stabilization is a little confusing in the sense that it's this cycle. It's not obviously all PL minus 1s have the cycle of the class of the point, but that's not what stabilizes actually. Here, when this constant in each of the PL minus 1s corresponds to the top cycle, so it's stabilized in some strange way, and this is the reason why this limiting thing, this xt, is sort of not a manifold, and it doesn't have a fundamental class. Like for example here, this thing, usually we think of this as a fundamental class, that you can, if you integrate of the manifold was, here, when you go to infinity, this kind of grows. This one, geometrically, the one at infinity in here doesn't really have a geometric sense, for example, right? So I say it stabilizes, but I'm cheating. If you take the element 1 in here, take the limit, it blows up, it goes to infinity, right? It doesn't correspond to an actual cycle. So for example, there is no intersection theory on this thing. We cannot intersect. It's like, so this is a little bit confusing, but we'll try to forget about this and we'll still get some amazing results. So that's one point, and maybe just so that we are a little bit more comfortable, I'll give you a few more examples, the similar ones as the last time, just so that you remember. So I remind you that we had some more examples. Actually, these are sort of the same examples, but maybe slightly more concrete ones. So for example, remember the simplest action. So for example, we can look at x to be just C4, and we'll look at linear actions. So to define a linear action, we will take, well, t is as usual as always C star. For today, I'm not going to do that differently. Then, of course, we can define the action in the following way, that I take t times some vector v, and then I define a linear action. So this t is always an element here. It's a non-zero complex number. And then here, it's a linear action, so I just give you a matrix. And so the matrix I can assume to be diagonal. This I explained last time. And so it will look, say, like this. It could be a diagonal matrix with these things. The group action forces the fact that these monomials should be just power functions where A, B, C, D are just some integers. Okay, so this is sort of an example of an action, but why I repeated this, I explained this last time in more detail, is that, of course, what we'll use is that this will induce actions on all of our projective spaces, Grassmannians, etc. So, for example, I can now, this induces, so I write it this way, an action on the Grassmannian of two planes in C4, right? So there is C4 as an action, obviously then two planes are also moving, so it's kind of obvious. So this induces an action like this. Now then, I also had another notation that I'll remind you just so that we have everything, and this is the fixed points. And so that's, for example, if you take C4 and look at the fixed points, then this will be pardon? No, C4 I'm first. This is a simpler question. The other one is the ones that are more difficult ones. So there's two questions, what this is and what this is. So, the origin, right? It's linear, so it's easy. There's only the origin that the v is 0, then it's fixed. So how many do we have? 4 choose 2, yes. So here we have the coordinate planes. So there is a 4 choose 2 elements, and they look like this. You look at sort of coordinate planes. So, right, I need to define two planes. So this is for all x, y, and c. Two planes. This is a two-plane, and then it goes, and the last one is this one. And it's all ways of choosing a pair of coordinates. So there's altogether 6 elements. Okay. So this is sort of a basic thing, but you see that it is simple action actually induces something that's already not so simple. It's just an example for that. And we'll discuss that. This will be our most important example actually eventually. And let's see what I wanted to say. So this I explained. AI. Yeah. Okay. So now let's just go, this is actually, you sort of did this, I think, in exercises, but let me now explain this more carefully. Is what happens if you, let's just take a simple example now, and more, one that's similar to this one, but simpler. So now I'm just looking at x equals, so C2, and this I mentioned before, t is always the same, and now tv is just equal to, and so the two numbers are now just 1 and minus 1. Okay, so the A is 1 and B is minus 1. This is the action, and then we can, this induces the action on the corresponding Grassmannian, which is now just P1. So now let's look at x equals P1. Maybe I won't confuse you with that x. Now x, I want x to be P1, and then a similar calculation, of course, shows that xt is just equal to, we discussed this last time also, 1, 0, and 0, 1. Okay? All right, so let's look at this action. So let's see do the construction, so what it does. Okay, so calculate now, for this one, let's calculate xt. I always put this in inverted commas because actually, it's, as I explained, you can sort of make sense of it, but you really care about the right? So, and these varieties are the ones that are very well defined. And let's calculate them. So what is happening, I mean, is that if you think about it, so I'll write down the answer. So then what you will have is that you want to see what XLT is. So again, so what this is that you take P1 with this action of the torus, and then you multiply it by CL minus the origin, and then the whole thing you divide by the C star action. And so what we'll be always using, that way now you will see, the problem is that here the action is not free. So then, but here the action is free. So what I'm going to do, I'm simply divide here and kind of sort of ignore this. And if you do that, you can easily convince yourself, then what you will get is the following, that I still have this thing, so I get rid of sort of the action with t, and then I just have a sort of a twisted version of P1. So you can easily convince yourself that what is really going to happen is the following. You'll have just PL, and then over PL, you of course have the bundle O of 1, and then you'll have also the bundle O of minus 1, or if you like, maybe let's use, these are sheaves. I like the actual bundle notation. So this, you remember, O of 1 I denoted by, O of minus 1 I denoted by S. So S was this universal subbundle. And then you have the dual of S, which is the dual bundle. So that corresponds to O of 1. So these were these two bundles. And then this corresponds to the projectivization of this is, of course, a projective bundle. So I'm sorry, it's maybe I'll make myself a little more space because now it's the same. So this you already know, but let me just give you, so this is more important. So I'll continue here. So this is equal to the following thing. So I have this PL minus 1, and then, so this is an exercise that you should think through, that you have O of 1 on PL minus 1, and you have O of minus 1 on PL minus 1, and then you take the direct, I did this, S direct sum S is dual, what I meant to say, and then I projectivize this. So this, okay? So this is a two-dimensional bundle, right? So we have on PL minus 1, we have our usual sequence, right? So this is S, CL, Q, and this is a line bundle, okay, the tautological one. Then you have this. Well, it's a two-dimensional vector space over each point. I projectivize, I get a P1 bundle. So that P1 bundle is precisely this XLT. Okay? So again, when I do, so what you need to verify is that here I take the usual action of the torus, the diagonal one. I multiply by P1, and at the same time, so it acts on both of them. But the way we are going to do this is that on each orbit here, which corresponds to the point in PL minus 1, since the action is free, I can sort of divide here first and see what happens here. And if you do that, it's easy to see that you precisely get this. Okay, so you easily convince yourself. Maybe the reason, maybe you can see it this way. It sort of corresponds to this. I think I did explain this sort of last time. This corresponds to the following thing, is that if you, maybe I should have given this example first, is that suppose I take a simpler example. So I look at I have the point, and now over the point, I look at the one-dimensional vector bundle, say acting here by, so this thing, t to the, so I look at this vector space. Yeah, so I just have the point, and I just have now, I have just C, and I really look at the simplest case now, one-dimensional vector space, and Tx on it by just T goes to T to the A, right? Now this is just a one-dimensional action. So then what will happen is that, again, I can look at C cross Cn minus the origin, right, and divide it by T, by this action. So now my manifold is C. And you can see, of course, that then, according to the same thing, I first divide here, I'll get a line bundle on Pn minus 1. So a PL, sorry, it's not N, it's L. Sorry. So it's PL minus 1, and you'll just get a line bundle on this. And this line bundle, this you can easily verify, is precisely O of A, or S to the minus A. Okay, so this will be a little exercise for you. I'm not going to do here. Maybe I'll ask you to check this. This is really easy. This just follows from the definition of the tautological bundle. Okay. All right. So and then if you extend this, of course, if you now, in a similar way, the way I got from here to the Grassmannian, now you can get from there to this definition. Okay. All right. So this will be one of our important examples. And okay, so then the next thing, next from here on, so these are our basic examples. So the simplest example, just the AT of the point, and that's just the polynomial ring. And then we'll look at things induced as linear actions. We'll have Grassmannians, projective spaces have induced actions, and there we will look at the Chow ring. So now, if we want to calculate the Chow ring, so I'll have several ways of doing this actually, but so what is finally, what is this? So this is our next project, so let's try to understand what this is. And so once we have this actually, we did in fact have a theorem, we didn't prove it, which did exactly this. We just calculated exactly this. So what we need to do is, of course, just to calculate the Chow ring of this thing and take AI of that, right? So it's a recall. It was a definition, the general definition, if you remember, the general definition of Chern classes. So you remember that there was two definitions, sort of. One was this degeneracy or linear dependence of some sections, but then, of course, that only works if you have sections. So I gave another general definition. We didn't work very much with this, so I just remind you what it is, but because well, now we need it. And so this was this idea that if you had some vector bundle, say E on X, then what we did was the following. To calculate CE, to define the total Chern class of CE, we do the following. We look at the projectivization of this vector bundle, And it's a theorem in topology and also in Chow groups that the Chow group of this thing has a simple expression by the Chow group of this thing. So this Chow group definitely has, because it's a projectivization, has an O of 1, so a universal bundle. So you just like always, we have a universal sequence S. So we have this sequence S, E, Q over this thing. And so this S thus is a line bundle over this. Okay, so there is a special element which is C1 of the line bundle. So we can look at C1 of S, and I'll denote this by this is a notation by, let's denote it by eta. And so I have, and of course each of the Chow ring of X you can pull back to P. So there's a map. So this is F, is a map from F star mapping the Chow rings of X to the Chow ring of E of PE. I'll not put the parentheses there, so make it, but it's the same thing, okay? And so combining these two things, the idea is, so the theorem definition actually, was the following, that this Chow ring, total Chow ring of this PE is just equal to the, I'm mismanaging the space all the time for some reason. Anyway, you don't erase anything, I have a longer thing. So the theorem is that the total Chow ring of PE is just the usual Chow ring, I mean the Chow ring of X, and then you attach this eta to it, a polynomial, attach a variable to it, which will be actually correspond to this eta. And then you just divide by relations, and the relation is that these, this is sort of the splitting principle, is that eta to the, sort of the rank here is some r, eta to the r, eta to the r plus C1 E eta r minus 1 plus etc. CR of E is 0. So that's the relation. Okay, so this is a definition of a definition theorem for the Chern classes. It's a theorem because I'm describing this completely. I claim that the Chow group of Chow cohomology of PE has this form, and it's a definition because it defines the Chern classes. So we have this. And so this is very useful now, of course, to see, because we have exactly this situation. We have somewhere here. This is what I'm going to study. So we have precisely now X is this PL minus 1. You have a bundle which is S plus S star, and we have the projectivization of that, and we would like to understand the Chow group of it. That's precisely what this ATP1 is. Right? So this ATP1, going back now, just the answer, right? To remember, this is the limit of this P1L, with that notation, T, P1L, A, P1L. That's what it is. And this P1L has this form. So let's just go on. So this P1L is, so the Lth is precisely this space. So this is just P of S plus S star. So this bundle E in this case is just S plus S star. And we just need to calculate, well, there we of course know the Chern classes. So of course these are line bundles now. So we know that C1 of, so E now in this example. So I'm using the theorem. So E is not just S plus S star. And so I just need to calculate the Chern classes of E. And so Whitney formula tells us that C of E, so 1 plus C1 of E plus C1, plus C2 of E is equal to 1 plus C1 of S times 1 plus C1 of S star. Right? That's the Whitney formula. And this is, of course, well, S is a tautological number, so here it's now using this zeta I used this is all happening on PL minus 1, right? And I'm calculating the Chern class of PL minus, of S of PL minus 1. That, of course, was minus 1, and this is the O of 1, which was plus 1. So this is just 1 minus zeta times 1 plus zeta, and this is 1 minus zeta squared. Okay. And so you just write down. So again, the theorem then tells us, again, so that this thing, this P1L, the Chow groups of this are just equal to, Chow cohomology groups are equal to, so I look at the cohomology of X equals PL minus 1. That's Z eta, Z psi, okay? And then we'll divide that by, and then I associate to this also, I add as a variable eta, and then I divide by a relation, and so one relation is that zeta to the L is equal to 0. That's one relation. And the other relation, that comes from the relation of PL minus 1, and the other relation is this one, which just says that eta squared, and then you just continue, eta squared minus zeta squared equals 0. That's the other one, right? Because here they are. You see C1 of E is 0, and C2 of E is minus zeta squared. And then I just put those things into this form. You get eta squared. This is 0, and the last one is C2 is zeta squared. Okay? So I get this formula. So, and then of course, I just take as I take the limit, L goes to infinity, the obvious thing happens is that this disappears, of course, as usual. And so I just get that the Chow groups of, the equivariant Chow groups of P1 are just equal to Z psi eta divided by the relation, this last one, that eta squared equals zeta squared. So you get some kind of funny symmetry also, you see. This is clear, right? So when I let L go to infinity, then this, just like in the previous case, it's the limit of the Chow groups of PL minus 1 go into just the polynomial ring. So it's actually kind of, you already get some funny thing here that I'll explain in a second. Okay? Is it clear so far what I'm doing? So, yes, so where am I? Oh, there's 9 more minutes, okay. Okay, so now what we are going to do today, for now, is just, I try to repeat our tools for this equivariant theory. So, our tools, and tools I mean for doing enumerative geometry in the equivariant case. So what did we do? case. So our tools were the following. So one of them was this Chow group business. We defined Chow groups. And then what else did we do? Well, we did intersection theory, which is essentially was the following. So we can, one of the important things was that if you had, remember, morphisms. So the one is morphisms. So the idea is that when you had x and y, right, you had an f, then well, for now, I'll assume that these are smooth. And this is not always important, but it's just so that you think of, I don't want to always specify the conditions, so everything is, the varieties are smooth. Then you had two things, right? So remember, you had f lower star, which mapped ax to ay, and f upper star, which mapped ay to ax. The pullback. This is the pullback morphism, the push forward morphism. And I put the dots here, noting that these are the same numbers now, right? So here's the same thing here, here's the same thing here. Same AI goes to AI, which of course don't correspond to each other because the difference between these two is exactly that codimension formula. Okay? And so the point is that you can say exactly the same thing in the equivariant case. There is no problem. So in the equivariant case, same. So what we are doing is, suppose I have two varieties with the T action, and the only thing is that the morphisms, of course, have to be T equivariant. So when I say morphism, then this has to be, in this category, the equivariant category, he has to be T equivariant. Right? So what that means is that if I take f of Tx, then this should be T of fx. I still have action on both of these varieties, and that should be compatible. Okay? So this, of course, is necessary. But if this is true, you can easily check, because it's basically, if this is true, then what you can easily see that you get a usual morphism from f mapping x L t to y L t. So in the limit, people say that x t to y t, but I don't like that because those spaces are not well defined, but these are well defined. So this just gives a map like this. You can easily verify. It's basically obvious. And this gives you maps then from the analogous maps. So, right, whatever I have there, A, X, L, T to A, Y, L, T, and F upper star, the similar one, the other way around. And then you just have to check that these things stabilize to define well-defined. So these stabilize, again, to give. So starting from here, you get the similar maps like that. So you get F no, but the equivariant ones. Well, we'll see examples, of course. Okay, so we'll calculate these maps. So the force of this theory will be, and I already want to explain this maybe now before I go on. So far it seems like we're just, chugging down, doing sort of the same thing in some other setup, but actually something important is happening here. So the force of this theory is, well, maybe let's just remember a little bit of this is push forward, pull back formulas and things like that. So, let's for example look at a simple situation. So recall, oh, maybe I have a little space here. Recall, so one case that will be interesting for us, and this is this push forward, pull back formula. So suppose x in this case, suppose x is a smooth embedding. Let's look at this case. Okay? So then, so, you know, for example, well, actually, it will be very funny. It will be just the interesting for us example when x is a point. That will be already very interesting. Okay? But so if that happens, then let's look at, then we can look at the following thing. We can push, so I just take x, the class of x, so that's the generator of a upper zero, if you like. And I push it forward, and of course that just gives you the cycle x in y. So this is really just x as a subvariety in the variety y, okay? And then I pull it back. Okay, so I pull back, and so this is, again, now a cycle in x, right? So the question is, what is this cycle? This is what I'm asking.
The degree of the map times x.
Pardon?
The degree of the map times another cycle.
So it's something of that sort. So let's just do it a little more precisely. So what is happening is the following. I mean, this is obvious what this is just as I said. But the pullback is less obvious because they're not transversal. So the idea when you do a pullback is more complicated. What you have to do, if you remember, you have to put, that was the first lecture, you have to put them in transversal position, the two things, when you pull something back, and then intersect. So you have to put x in transversal position inside y to x itself. And then that intersection, that just gives you a cycle in x. And that's what it's going to be, okay? And it's, in some cases, when this alignment is actually a degree, in fact, but you will see. But so, actually, if you do it locally, it's completely clear what you have to do now, because, so the way it looks like, this is y, and this is x, right? And now, what does it mean to deform x inside y? Well, it's the obvious thing. I look at the normal bundle, the normal direction here, and, you know, in the normal direction, I move the point a little bit, right? So actually what I do is I look at a section of the normal bundle of x inside y. So if you remember this sequence, the tangent bundle of x is the tangent of y, and the quotient is the normal bundle. Okay? Everything is smooth now. And so a deformation, the most obvious way is just to go in this normal direction, because if you move in the x direction, you're not moving x away from itself. If you want transversality, this is what you do. And of course now, what is the intersection? So this is a local dish. What is the intersection? So this I, so this is a self-intersection, of course. It's basically, if you like, it's the pullback, it's sort of x intersection x. Right, that's what it is, inside y, and then that's pulled back in x. But that's what this really is going to be. So when is the intersection is happening? When this section is 0. So this is just equal to gamma equals 0 inside x. That's the cycle. And what is that? Not C1, it's yeah, that's a little confusing always, it's Chern classes, it goes the other direction. So C1 is actually the most complicated one, and C top is the easy one. So it's the top Chern class of it. I didn't say the dimensions, so you don't see them now. So let's, maybe this is dimension, say, well, just codimension, anyway. So, and this is, so gamma 0, of course, by definition, is simply C here you have the codimension of X inside Y of the normal bundle of X inside Y. Okay? So that's then one of the things that we sort of used. I think we had some examples. But so, of course, the point is you need the dimensions here. So say if I take a point, then what happens? So suppose X is a point. Well, if you look at the point, well, it will have some, well, already the formula tells you what happens, which is that the point, the Chow groups of the point are just in dimension 0, and this codimension is bigger than dimension 0, so you'll get 0. So in this case, of course, if dim y is greater than 0 and X is a point, then of course this is I upper star, I lower star of X will be just 0. Of course, because of dimension reasons, right? So that's obvious. And also you see it in geometrically, because if it's just a point, you can easily deform it so that and they don't intersect anymore. You're done. Now, what happens in the equivariant case? So you do precisely the same thing. So, for example, I take P1, for example. I take P1 and I take a point. Now, the point, first of all, so now we same question in the equivariant. So let me just the sequence is important here somehow. So, yeah. So I'll continue. Actually, no. So there's this thing that I have to do at the same time. So it's just a simple thing, but maybe I'll continue this thought. For example, so I'll just ask the question now. The question, so in the equivariant case, what happens? So for example, now if I take P, I'm out of time, right? Yes. Okay, I'll ask the question, then I'll stop, okay? It's just so suppose I want to calculate the same thing now, okay? But so what does that mean? So I have this P1 with our usual, the action that I fixed, this TT inverse. And you remember there are two fixed points, the 1, 0 and the 0, 1. Now, the point is that when you want to have equivariant maps, then you can't have arbitrary points embedded, because that's not a morphism, right? So it's only the fixed points that are a morphism. So I mean, when I say point, if I want this to be an equivariant map, so I'll call this F, point equivariant, if and only if, of course, F of the point inside P1 is a fixed point, right? Because otherwise the thing moves, so it's not going to be equivariant. So in fact, there's only two maps. So if you look non-equivariantly, then you have lots of maps of a point into P1, but equivariantly there's only two maps, the two fixed points, okay? And so the question I'm asking, okay, so let's take one of the fixed points. So what is this thing? Well, there are two cases for the two fixed points. What is that? So there's just two things why this is not 0 anymore. So one is that, of course, now the equivariant cohomology of the point is infinite dimensional. It's a polynomial ring, so there is no reason, there's no dimension reason anymore, right? Remember, the equivariant cohomology of the point was this z psi. So now it has degrees in every dimension, so this formula will not. So that's one thing, and the other thing is this deformation argument with the point. As I said, now there's no deformation anymore because you can't move the point away because then it's not going to be equivariant anymore. So the point is stuck. So that argument also doesn't work, this self-intersection one. So, okay, so I'll continue from here. Shall I continue? Okay, so again, so we are just chugging through what we've done in the usual case of those basically three main concepts that we had. But for this, what we did in the non-equivariant case, now we are doing that in the equivariant case. So those were just definition of Chow groups that I did, and also the Chow ring structure on the Chow cohomology groups that we defined. Then the next thing was the morphisms in this category, and the corresponding push forward and pull back things. And since they are directly, because of this story here, they directly analogous in the sense that once I have an equivariant morphism, again, that's this condition, then this immediately gives us morphisms between these XL, YL spaces, and then I can use all the formulas that we had, so also the permanence formula, push forward, pull back formula, etc. And in fact, this formula that I wrote down here will be also true, you will see, but now, because the equivariant cohomology of a point is not zero-dimensional, this thing will not be zero, okay? And this will be important. Maybe just, I'll have to erase this, I think. I'll just make maybe 2 more remarks about this. Also you understand as students the status of this, though I'm not proving most of these things. I'm giving the constructions precisely and statements about these constructions, some of the things we are not verifying. Like I'm saying this limit exists and that's what it is. It's clear in the examples, but I'm not proving it for any variety. Where I'm explaining the construction, we will be making calculations using these constructions, using the theorems, but I'll not ask you to prove any of the theorems. So there's really very few proofs in this part of the story. I would like you to understand the definitions, use these definitions to construct things and calculate things. So that's what we are doing. Okay, but the definitions are precise, however, so it's not vague, but the proofs are not really here. Okay, I'd like to make 2 extra remarks regarding these equivariant push-forward, pull-back things. So, or maybe even 3. So, yes, so first some extra. So the first thing is this push-forward, pull-back formulas, so, or permanence, it's also called. I just remind you, we had this formula, and it's exactly the same formula as true here. So the permanence was this idea that if you had some f x, y, then basically the idea is that under the pullback, so we have this map. So you simply have this map, but it's more than that. It's this AX under this becomes a module over AY. So you can take an element here and you can multiply things by it, and this becomes a module over AY. So these are both rings. So makes AX and AY module. And so the actual formula for that was the following, is that if you, say, took an element alpha here, well, I will not see where they are, they'll be obvious from the formula, so you took an element alpha on the right-hand side, and you pull back f star alpha, and you multiply it by some beta, which then obviously is an element in x, so alpha is in y and beta is in x, like I'm showing you, and you push that forward, then it's the same thing as if you just, so this thing is kind of, gets canceled, that's the permanence. So it's the same thing as if you just push forward just beta, and you multiplied it by alpha on the right-hand side. So this is now, both of these objects are in here. Okay, so this is this permanence. And one important example for us is the following, is that, of course, as I said, it's obvious, but it's a non-trivial thing to have a morphism of a point into a variety, an equivariant one, because it has to be a fixed point. The other way around, although it's completely obvious, is that you can always, so if you take x with an action of t, then of course X point is always is an equivariant morphism. Right? Because, well, it's obvious. Okay? It satisfies that definition, since all the definition happens on the point side and there nothing happens. So it's easy. And so this gives us several things. So first of all, it tells us that the equivariant cohomology, so this gives us that the equivariant Chow groups of X are morphisms, is a module over the equivariant of the point, which is just this z eta, the xi. Right, so this was also true in our example, if you remember. If I still have it here, no, I already erased it, the answer. But it's always true, right? So remember, for example, this A example, this A, you already have this, I just repeat this. P1 was this thing, Z, zeta, eta, zeta squared equals eta squared. Obviously, this is a module over Z eta. So this is a module in a natural way over Z eta. Z zeta, sorry. Okay, so that's one point that we get out of this thing. So when you have equivariant Chow, these equivariant Chow cohomology groups, they are always not simply a ring. They are a ring where the well-defined action of this zeta element. And that's natural. I mean, that's not so surprising because you remember this comes from the fact, if you like, that yes. So this I would like to explain this now. Is that actually, as I explained it in the so this comes from the fact that when you look at this X. So I continue now for this general X case. This XL T thing, then it naturally was a bundle over PL minus 1. Remember that was because, remember what I was explaining was that you look at X cross CL minus the origin and you divide it by C star, and you can do that. So what will happen if you do this? It's similar to what we had before with that P1 case. Remember, we did this for X equals P1. So what will happen is kind of amusing. You will get a bundle. So this is XLT, right? So I can, as I said, it's obvious, right, that you have a map from this product to, there's a well-defined projective element corresponding to this thing. So you definitely have a map from here to PL minus 1, and you divide. So this XLT is maps over PL, and what is the fiber? Okay, so what are the fibers of this map? Well, the point is, once I did this, I completely got rid of the action. So the fiber is X, actually. So that's what was also the case before. Remember, the fiber was a projective P1 bundle. So you have this amusing thing that this XLT, the way to think about it is that you have this PL minus 1, this growing PL minus 1, and the fiber is a fiber bundle over PL minus 1 with fiber, which is X. And then you have to blow up the L go to infinity. That's the picture. But this, of course, immediately explains this, why this is true, because Z xi is the Chow group of this, and then, you know, that, of course, when you have a map, a fiber bundle like this, then its cohomology is a module over the cohomology of this thing. So this statement follows from, or that statement follows from here. Okay. Well, maybe it's enough remarks for now, so I'll do the next thing. So we had one more thing. You remember one more tool which was very important, which simplified calculations and was really very useful in many ways. And this is bundles and Chern classes now. And that also works perfectly smoothly. No effort, works perfectly well. So let's just see what we need to. Again, we have to be just a little careful, as with morphisms. Morphisms had, of course, a condition that they had to be equivariant. Well, of course, bundles also have to be equivariant. So the idea is that you have now Ex, and now you have to have an action of T on the whole thing, on the bundle as well, of course. Okay? So let me maybe, let me just first define everything. This is easy. So the point is that the claim, okay, is that, so this is an equivariant bundle, that one can define equivariant Chern classes. So one can define this way, and the way is kind of the obvious thing, which is essentially we already done this with this construction, is that this thing, in fact, so how? Is that, in fact, from this, we can simply construct a bundle over XL, right, with the same mixed construction. So we just look at E cross, so what will happen is that I'll look at E cross CL minus the origin, and this, there is an equivariant map, so obviously here it is. Okay? So we have an obvious map, since this is trivial and this is E, so there's nothing happened. But now I divide both sides by T, since this map is equivariant. Right? So this map is equivariant. So you understand what equivariant means here, right? That it's in the same sense as I already defined equivariant. Then T, if you act by T here and map here, is the same thing as if you map. So it commute the T action. So in this, it's just the bundle is just an equivariant bundle is a map which is a bundle map in the equivariant category. So that equation is true that it commutes with the action of T. Anyway, so we're here, and now what is this? This is of course just XL T of XL, no, not like that, XLT, like that, right? That was the notation. And then here you have some ELT, which is that thing, and then this is a bundle over this. And it's just the Chern class of that bundle, that's all. And then you take the limit and it stabilizes. Again, you have to verify that what it says. So this thing is simply equal to the limit in the same sense as always, as L goes to infinity, of the I's Chern class of this EL T. And that's all. So in a certain sense, this is now, I'm just repeating, since in a certain sense we already done this, but let's just do this again. So as an example, say the simplest thing is, let's just take the point, as I said. So let's take the simplest equivariant bundle. Already gives you something not completely trivial. So let's look, for example, X is the point. This is what I just, X is the point. And so say the bundle E is now just a module over the point. So it's just a linear action. So E is just, say, C. It's very simple, just one-dimensional, say, for now. I just have to define the action. So T acts, so T V is equal to T to the A V. So that's the action on E. And of course, on that point, the action is trivial. So this is an equivariant bundle over a point. So this is something very simple, right? Okay, and so this is what I just told you like a half an hour ago, is that actually it's easy to verify what this bundle is over this, that this actually gives me So PL minus, so of course we know that XL is equal to PL minus 1, and EL, that's what I was saying, is just a bundle now, which is just S, so this is now, I think it's, maybe it's S to the A, no, I don't remember, I have to, yeah, it's S to the A. S, so I mean tensor power. It's a line bundle, the tautological line bundle, SPL minus 1, and I think it's S to the A. So and there's a convention there, which well, you'll do an exercise and then you'll see precisely how this works. Okay. So that's what it is. So usually the tensor I emit is just S to the A. Okay. So yes, so in this case, then if you look at what I want to say. Yes, so what is the Chern class? And then so what is the Chern class, the equivariant Chern class of so it is only a first Chern class because it's a line bundle of this E, or will be, it has to be in that polynomial ring, you remember Z xi, and this should have the correct degree, so it's degree 1, so it will be just a multiple of this, and so this is an A, but now I have to check what there's a convention that I'm not remember, it's plus or minus A, so I'll fix this in there. I think if you choose that, you can, there's a certain convention you can choose. I don't want to explain this now because I didn't prepare this. For this action, and then on that it depends whether it's A or minus A. I mean, it's natural to take A. Yeah, well, let me, for at least it's a blackboard, I'll make a choice, okay? So let's call this minus A, and then it's A, okay? Like, so remember, S, the Chern class of S is minus xi. It's a dual, as a tautological bundle is minus xi. Okay. So this is this equivariant Chern class business. And then, so I'll make this choice actually. Okay. And so maybe let's just do some fun thing now, is that the Whitney, everything is true. I mean, as I said, because you pass through this E, so the sort of the axioms of Chern classes hold. Chern classes hold. So there's two important things. Remember, is naturality. So this means that if you have, you remember, say, X, Y, you have a bundle E here, then of course you can pull the bundle back to, this will be now a vector bundle, and so naturality tells you that the naturality condition is that if you take the Chern class, so you can do things. You can take the Chern class of E here, the total Chern class, say, so I take of E. So this is in Y, and then this is in the Chow groups of Y, and then I can pull it back now, right? And now I end up in X, or I can just take the total Chern class of this pullback bundle. So this equality is the naturality. So a quick example of this would be, say, if I just take a bundle that is trivial. So for example, we will need this example, in fact. So let's look at, you remember I have this P1 and my favorite sequence S. Then you just have C2. And then you have Q. This is the tautological sequence over P1. And I can ask you now, what is the total Chern class of this C2? Okay, over P1, but now I'll ask you for the equivariant Chern class of C2. Yeah. So here, as usual, as now I'll always assume is doing today's lecture, is that we have this usual action. So T x y is Tx T inverse y. So we assume that. Okay? So this is the action. The action on C2 is this. T goes, so T on xy goes to Tx T inverse y. This is the action on C2, which induced that action. Remember, this we take the same. So the question is, so what is then, if I take this trivial bundle of P1, what is its total Chern class? So remember, when you have a usual trivial bundle, then its Chern class is 0. I mean, it's 1 and then nothing. So the total Chern class is 1, actually. 1 and then 0, 0. The zero's Chern class is 1, and then the rest is 0. But what is it going to be here?
The action on the fiber side is trivial. I mean, if I have the trivial bundle.
Yeah, so I'm cheating now. I mean, not cheating. I'm being imprecise here. This C2 is this C2 here. So if you like, I put a T here. Okay. So sorry. Of course, it's not trivial. So what about this one? Okay.
Well, the action on P1 is trivial? Or?
No. The action P1 is written here. And actually C2 it's what we did in the first hour. So you have a vector space that's C2. And on that, I define a linear action. Here, the weights are 1 and minus 1. And that induced an action on P1, remember? And that's this action. So this is one that has two fixed points, the 1, 0 and the 0, 1. But now I have a sequence SC2Q, which is now equivariant. All of these three things are equivariant bundles. Now it's easy to see. And because it's the tautological bundle, so it's in C2. It's a point. Actually, what is S? Is a point in C2 such that it's on that line that corresponds to P1. So it's the total. So obviously, it's easy to see that this sequence is equivariant. I'll get to that in a second. But now I just wanted to say this simple thing that let's just take this C2 trivial bundle over P1 with a non-trivial action. Nevertheless, what is its total Chern class? Equivariant Chern class.
1 minus xi squared.
Right. So the point is that I'm trying to use this naturality condition because the point is that this is CT. So C2 T on P1. This is actually equal to the pullback of just, well, I don't know, the same notation, of course. Let's say C2 T from, but now meaning something else, meaning that F maps P1 to the point. And what trivial means that I pull back the bundle from a point, but on that point, the action is not trivial now, but this action that I just wrote down here. Okay? And there, of course, we calculated what it is. So the Chern class of a line bundle, remember, is just the two weights. So I took this convention. So that means that here, so maybe over point. So I should say C2 here point and C2 here P1. Okay? So now the total Chern class, the equivariant Chern class of C2 C2T over a point, okay, like that. So this is a direct sum of two line bundles, the two that I defined. So this is just the Chern class, the total Chern class. So here is Whitney. Says that this is just the total Chern class of, and now I do this calculation, remember? So now I have a point, and I have some T to the A line bundle, and their answer was this thing. So it's C of C now over a point, and here with weight 1, and then the same thing, C. So it's that example, but now with weights 1 and weight minus 1. It's the direct sum of two line bundles over the point. Okay, and so according to that thing now, this should be just 1 plus zeta, so plus 1, times 1 minus zeta. So it's minus 1, the two weights. So it's that formula here, this A. In one of the cases is plus 1 and the other is minus 1. And then I take the product because this line, the vector, this two-dimensional vector bundle is the sum, direct sum of those two one-dimensional. So I get 1 minus zeta squared, as you said. Okay? And then the point is that what this naturality says that that's actually the same, that this should equal to that. And it's, so this is going to be this element. So now this naturality finally tells us that, this C, so this thing here, the C, total C of T of C2T over P1 now, this thing is just going to be the same thing because it's natural, 1 minus zeta squared as an element in the equivariant Chow groups of P1 now, which you remember is this ring Z, Xi, so zeta, eta, divided by this relation that zeta squared equals eta squared. Okay? That's the calculation now that we've done. All right. And now we'll do another amusing thing. So that's the following. So allow me to erase this so that I hope this is clear. Which is that I'm going to use now. You remember how we could construct, in fact, and this is true for Grassmannians, it's true all Grassmannians, that we can construct the cohomology or the Chow groups of the, say, the Grassmann or P1 using the, so maybe I'll re-explain it once more so that it's clear. So cohomology or Chow of P or Grassmannians, for example, or any flag varieties, this works, from tautological sequences. This is a very important calculation. Okay, so let me remind you just for really the simplest one is P1. Okay, so P1, how did this work for P1? P1, so I have this tautological sequence. Okay, so non-equivariant P1. So then I have the tautological sequence, and I have this line bundle here, S. So let's just call, well, it's minus zeta, unfortunately, that's a bit annoying. So zeta is just going to be equals just the C1 of S. So I take this tautological sequence, and I construct cohomology elements in the Chow group, Chow cohomology elements using Chern classes. And then I find relations now. So how does that work? So I remember this calculation. It works the following. Let's call it actually eta. I hope it's correct. Eta, which is yeah, it's a bit annoying now. Just a second, zeta. I did this, but somehow, well, I think it's correct anyway. So is it just going to be, sorry, it's equals to C1 of Q. Okay. So what do we get then? So it seems like, you see, I just use very naively. I want to do as many cohomology classes as I want using Chern classes. So I have P1, I have this sequence, I have two bundles I see here. Great. So I have C1 of this is C1 of the other one. Okay. And I look at this polynomial ring generated by these two. I suppose I have a theorem that they generate, okay? But what is the relation? The relation is Whitney. So Whitney says that 1 plus C1 of S times 1 plus C1 of Q is equal to the Chern class equals to 1, which is equal to the Chern class, or if you the other way around, equals to the Chern class of C2, which is now non-equivariant, is trivial, so it's just 1. Right? And so this gives me what? If you calculate it, it tells me that the sum of these two is 0, and the product is also 0. So this tells me that eta plus zeta is 0, and that eta times zeta is 0. That's what it tells me. And that, of course, just means that it's a trivial, if you knew this, that you can eliminate one of the variables using this thing, and the other, and it just says that it's the same thing as zeta with the relation that zeta square is 0. And that's precisely the Chow group of P1. Is zeta with zeta square is 0. Right? And so I'm trying to say that let's just do that again, but now in the equivariant case, we get something very funny. Well, so I'm sorry about this. This sign thing is a little, anyway. So, 51, so I still have time. So let's just do the same thing equivariantly. So equivariant P1, now the calculation. So I have the exact same sequence. I write down exactly the same thing. The only difference is that now the CT is not what is this. So when I get to here, so this actually doesn't change because this changes because CC2 is not 0, it's this thing. So let's write that. So, yeah, sorry, so I screwed this up a little bit. Sorry. Yeah, now I see what I did. It's just there's so many of these things around that, yeah. Well, you'll see it's kind of silly. Yeah. Okay, I'm sorry, yeah, I screwed this up, yeah. So it's just everything is correct, but the notation is not. So alpha, let's just make it alpha beta, okay? Sorry about that. Yeah, no, I understand. I did something silly. So alpha plus beta is 0. Alpha times beta is 0. So please correct this. So, and alpha, the result is that if once you eliminate beta, that A P1 is just equal to polynomials in alpha with the condition that alpha square is 0, right? Okay, so let's just do that. It's easier because otherwise these zetas get confused. Okay, and so now let's do the calculation, the exact same calculation. I get to the very last point and I get the following thing. So I get that 1 plus alpha times 1 plus beta is equal to, so this is now, I just repeat, I have this equation and I just replace this by alpha and this by beta, and I just equal to this. And this is equal to 1 minus zeta squared. That's what we get, right? That's the total Chern class of C2. Okay? And so what are our equations now? So our equations are that alpha plus beta is 0. So it's the same thing. I can eliminate beta again. And alpha times beta is equal to zeta squared. Those are our equations, right? And now let's eliminate beta. And what does this say? So I eliminate beta, and this is, of course, this ring now. It says that the equivariant P1, if we believe that this generates, so with the same assumption, is just equal to, so I have Z, I eliminated alpha, so I get alpha, and of course zeta, which is there. And then, because, yeah, that's always there now, because as I said, this thing here, somewhere it was here, no, I already erased it, that you always have Z zeta there. It's always a ring over Z zeta, the equivariant Chow ring. And the relation is that alpha times minus alpha is zeta, so that means that alpha squared is equal to zeta squared. Right? And of course, this is precisely what we had before, if you remember, with that other way. So, yeah. All right. And so now, finally, we sort of have everything. But, so I thought I will not get to that requires a little more work. So we do finish it next time to actually do the formula, the amazing formula that the localization formula. This is now very close, so I'll explain just the main detail now that we can now do. Maybe I'll do it here. And this is what I promised. Let's calculate this push forward pull back formula now. So the question is very simple. It's the following. Now, say let's just take P1 with our usual action. So the action that I defined. So P1 T. So I'm not writing this down, but it's the same action as before. And you remember now, and there's also the point also. And now between these things, actually, there are three morphisms, if you like. I mean, there's a point can be mapped here to the North Pole, to the South Pole, and of course you have the map in the other direction. That's it. So between these two spaces, there are only three morphisms, actually. Okay, but so what interests me is, so there's actually two, well, let me write it this way. Maybe it's the embedding of the point. And now I have to say something here, so I'll just, well, it's an ugly notation, but I'll say, oh, this is really bad. So, well, yeah, let's call it N. That's also bad. This I didn't think through. Right, so I want to, okay, so there are these two fixed points, right? The thing is rotated like that. That's P1 is a sphere. Okay, so this is the North Pole. Okay, this N, I'm going to take this N now. And the side, maybe capital N. Okay, capital N and capital S. North Pole and South Pole. Okay, so North Pole is going to be 1, 0, and the South Pole is 0, 1. And so then I have this obvious embedding. So I'll call it A iota north, just like this. Well, I don't know where to put it. I'll need the indices. Iota north of, let's just call it N. Okay, sorry. Let's just call it N, which maps the point into P1, and N of the point is just N, is this North Pole, and then the other is the South Pole. So this is sort of obvious morphism. So this is an equivariant morphism. And what interests me, as I promised, we would like to calculate So we would like to calculate the following thing, N. So I would like to push it forward and then pull it back. That's the question, what this is. And so before, as this is what I did the calculation for the points, and it was completely trivial. But so now it's not going to be trivial. So I don't have much time, so I'll just tell you the answer. So the answer is that this is just the sort of the weight of the tangent bundle. So this is equal to, now this is something on a point. So one way of understanding this is that it will be just the same thing as before in a sense. So it will be just the total Chern class of the normal bundle. I mean, at the top Chern class of the normal bundle of, so it's a different N unfortunately, of the point in P1. I mean the North Pole actually, North Pole in P1, right? So I'll explain this next time. I decide if I give it an exercise. But so here is P1, the North Pole. Here there's the tangent bundle. Of course, the normal bundle is the same thing as the tangent bundle. And the top is just 1. So it's C1 of the tangent bundle of P1 at the North Pole. That's what it is, right? So the normal bundle at the North Pole of N of the North Pole in P1 is just a tangent bundle of P1 at the North Pole. And this top is 1 now because that's the dimension. Okay, and so we calculate it. So you have to, this is a one-dimensional vector space on it, and you have to know the weight of it, and you calculate it, and it's 2. So this is just 1 plus, so it's just 2 zeta, okay? because the weight is 2. So we did this. It's 2. But just to finish, this is now a little bit of a magic, but one can really do this completely honestly by hand. And this is, I don't have time now to explain, but in the sense that I can just simply take well, anyway, maybe I'll give this. I'll give you as an exercise. This is simply very easy. Okay. But anyway, this is the answer, and then this pushback pullback formula will basically is what localization is. I'll explain this next time, which means that you can calculate intersection numbers on the whole of X from information intersection numbers at these fixed points. So you can reduce everything to points and to projective space, basically. Okay, so I'll explain this next time. Okay.